In this lesson, we'll be looking at how systems at equilibrium respond when that equilibrium is disturbed. I like to use the analogy of a seesaw to illustrate systems at equilibrium. When the seesaw is not level, as it is in this picture, the system will increase the rate of either the forward or the reverse reaction in order to reestablish the balance between the reactants and the products. So today we're going to be looking at how changes in concentration, temperature, and temperature each affect the equilibrium. So the principle that is used in order to explain why reactions do this is called Le Châtelier's principle. So it says when a stress is applied to an equilibrium, the equilibrium will shift to alleviate the stress. So here we have a reaction. We have the reactants are essentially colorless. Iron 3 is actually kind of a light orange. The thiocyanate ion is colorless. And then the product that they form is dark red. So when you have them, the reactants and the products in equilibrium, you're going to have a light red color. The reason why this one is very useful for showing equilibrium is because the more products you have present, the darker red it's going to get. So it makes a very nice visual. So we have our little seesaw picture there. We have a higher concentration of reactants than products, which is perfectly fine. It just means this reaction is a little bit more reactant favored than product favored, at least the way I have it drawn. And then we're going to increase the amount of reactants. Now this reaction is really, really fast, but if you could see it, now that we have more reactants, we're going to have that light yellow orangey color that would go with having some having the overabundance of the reactants. So then the reaction is going to increase the rate of the product formation in order to reestablish equilibrium. When you are using the seesaw analogy, whichever end ends up sticking up is the side it's going to shift to. So it's going to shift right to make more products. So if you make more reactants in order to establish equilibrium, reestablish equilibrium, that's a left shift. And if you, like in this case, go the other way, make more products, that would be a right shift. And in the illustration, we can see that because we have more products, even though it is now at equilibrium again, we have a greater concentration of products, so the color ends up being a little bit darker. And this is actually a very common lab that is done, so this is something to look for if you end up doing this lab. So other ways to cause a Le Châtelier shift would be if you had a gas phase reaction like we have here, and you want to change the pressure on the system. Now remember, the reactants and the products are in the same flask. I always have students asking me what side we're adding the pressure to. So we're going to adding pressure, increasing the pressure on both sides. So I've got to turn my pen on. All right, so this one actually does not use a seesaw idea. Instead, I always kind of describe it as being a funny looking water balloon. So over here on the reactant side, we have 3 equivalents of hydrogen gas, 1 equivalent of nitrogen gas, and then on the other side we only have 2 equivalents of the NH3 gas. So that means that if this were like a water balloon, the left-hand side of the reaction is going to be much larger. It's going to take up more space than the right-hand side. So there we go. So if you start increasing the pressure on the system, it is going to affect the reactant side more than it is on the product side. And so you're going to end up with a right shift over to the side that takes up less space. So yeah, that would be a right shift. Let me see. So highlighter. So the next one, NH3 increased. I'm going to go and erase this. There should be a way to get rid of all of it, but I can't think of what it is at the moment. So if we have increase in the amount of NH3, that means we're making the right-hand side of the equilibrium heavier, which means it's going to shift like that. That's just the board for the seesaw, which means it's going to shift in the direction that is pointing up. So it's going to be a left shift. And then heating temperature increased. So again, let me erase stuff. So when you go to do temperature and it indicates you have a thermochemical equation, just pretend that heat has mass. It does not have mass, but it makes the seesaw part of it work a little bit easier. So we're adding a component to the left-hand side, which means that we're going to have the seesaw tilt like that. So it's going up on the product side, which means it's going to be a right shift. All right, so let's look at some more examples. So here we have another pressure increase. So we're just going to look at how many moles of gas we have. So we have 1 plus 2, so we have 3 moles of gas on the reactant side, 3 moles of gas on the product side, so they both take up the same amount of space. So that means in this case, there will be no change. You don't always have to have a response. Heating temperature increased. So here we're given the information about what the enthalpy change is. So you can see that this is an exothermic reaction, which means heat is on the product side. So if we increase the heating temperature, that means we're going to have a left shift. And then H2 removed. Oops, wanted to erase that. So now in this case, we are making the product side lighter. So kind of imagine the seesaw with your pen or pencil. I usually see people using their pencils. So we are tilting the right-hand side up, which means it's going to be a right shift. And then CH4 removed. So that means now we're making the left-hand side lighter. So it's going to be tilting up on the left-hand side, so it'll be a left shift. And then catalyst added. This is a favorite question to ask because actually a catalyst is not going to it's not going to cause an equilibrium to shift. It causes the rate of the forward reaction to increase just as much as the rate of the reverse reaction. So the ratio ends up being the same. So that would be a no change. All right, so we got another one. We got the gas phase reaction. So we got 3 moles of gas on the reactant side, 2 on the product side. So ask yourself which way it would shift. Hopefully you said with a pressure increase it would be a right shift. Volume increased. Now you got to think back to the gas laws unit where we saw that pressure and volume are inversely related. So if increasing the pressure causes a right shift, that means increasing the volume will cause a left shift. You're making more space, so it's going to shift to the side that takes up more space. And then this one is a heating temperature increased. So we look over here at our delta H. We see that it's positive, which means it is an endothermic reaction. So heat is going to be on the reactant side. So that means it will be a right shift. And then N2 removed. So we're taking taking an N2 away. Make sure you're looking at the right component, the right substance when you do these. So that's going to make the reactant side lighter, so we're going to end up with a left shift. All right, in this next part, it's a really short clip from a children's video called Uki. I have to warn you ahead of time. I've shown this to college students. I think it's really helpful. Showed it to some college students. They got really bent out of shape that I would show them something meant for 3-year-olds. So I'm just giving you a warning ahead of time. So in this video, we're going to have a system at equilibrium. So our system at equilibrium is shown with a seesaw. We have an animal on either side of it. They're going to be going back and forth at a nice even rate. And then we got this squirrel, who is the stressor. So let's go ahead and get this started. All right, so we've stressed the product side, and now we are no longer in equilibrium. So we're going to try to have a temporary solution by doing a left shift. All right, but now where the equilibrium is still stressed. All right, so that doesn't really work, because if you stress one side, you're actually going to end up making more of either your product or reactant. Right, so equilibrium has been reestablished. We have more reactants and more products. All right, so that's pretty much all I have for Le Châtelier's principle. So we saw that Le Châtelier's principle is that when a stress is applied to a system at equilibrium, the system will shift to reduce that stress. And a shift is going to be either increase the rate at which products are being formed or increase the rate at which reactants are being reformed. Concentration changes. If you add reactants, it causes a shift towards the products. If you add products, it shifts left towards reactants. And remember, you can just use the seesaw, and then whichever way is pointing up is the way it's going to shift. So if you add reactants, you end up with the seesaw tilting up to the right, so therefore it's going to be a right shift. If you add products, it's going to be a seesaw tilting up to the left, so it's a left shift. Works the same way if you remove products. We saw that if we are using temperature changes to stress an equilibrium, you just pretend that heat has mass, and that you pay attention to which side of the thermochemical equation it's supposed to be on. So if it's exothermic, it's a product. If it's endothermic, it is a reactant. And then do the same thing as you did with the concentration systems. If you have pressure or volume, you have a bunch of gases, that's where you have to imagine you got the water balloons, and the size of the water balloon depends on how many moles of gas you have. So if you increase the pressure, it's going to shift to the side that takes up less space. If you're talking about a change in the volume, just remember that pressure and volume are inversely related. And also, if both sides have the same number of moles of gas, then there's not going to be any shift. It's going to affect both sides equally. Likewise with catalysts, because they change the rate of the forward reaction just as much as they do the reverse reaction, again, there is no shift. There is no overall stressing of the equilibrium. All right, so that's it for Le Chatelier's principle. Thank you for listening.